Okay, so we were just talking about this graph before I get cut off. We were talking about what does it look like. Well, at high resistance, there's low current, but the full EMF. So the low current, multiplying that EMF by that number, because power is potential difference times current, means that the overall power is very low. What about at very low resistance? At very low resistance, you're getting a decent current, but the potential difference is very low. The terminal potential difference is very low, so you're going to get low power as well. And you can see in the middle, there's going to be a peak. Okay, and then what you can do using your math skills is you can differentiate this curve. So if you differentiate this function, you'll learn about that at A-level maths. If you're studying A-level maths, you can find out when that peak happens, and it just so happens that that peak happens so you get maximum power output from the resistor when the external resistance R has the same value as the internal resistance, little r. Okay, so that explains that fourth graph that we did in the experiment, and it gives it kind of a mathematical underpinning. So that's why it happens. Okay, all that leaves me to do then is put up that summary of internal resistance. So I'll just go through it. So batteries have their own resistance, okay, called internal resistance, which is the lowercase r. That means a share of the battery's EMF is taken up across this internal resistance, called the lost volts. So that share of the battery's EMF that's actually across the battery's own resistance is called the lost volts, and that's the equation for lost volts. Okay, here's the key equation, which is exactly the same for any potential divider circuit. The EMF is shared between one resistor and the other, terminal potential difference in the lost volts. That can be rearranged to produce this, which is the graph of the experiment. The gradient of the graph, it's a linear graph with a negative gradient. The gradient gives the internal resistance and the y-intercept gives the EMF. And then finally, in summary, if the external resistance in the circuit is really high, so high external resistance, then the full EMF is across here, but there's low current, so there's low power output. If the external resistance is turned right down, then this resistance becomes significant, and this resistor gets a bit of a share of the EMF, so the lost volts is significant. So the power output is low because there's not much power across this resistor. But if you get the value of the resistor just right, so it matches the value of the internal resistance, then you'll get maximum power output from your circuit when the external resistance has the same value as the internal resistance. And that is the end of internal resistance.